Kate, starting new series on YouTube named What Paper I Have Read This Week. In this week, I have read a paper called An Image Worth 16 cross 16 Word. Its short form of this paper is Vision Transformers. So let's start. Before proceeding to this paper or before reading whole paper, I just read the abstract introduction and conclusion, and then I get a whole overall understanding of what this paper is basically is for me. So let's start. An image was 16 cross 16 word and transformer for image recognition at scale. While transformer architecture has been de facto standard in the natural processing task, its application to computer vision remain limited. Yeah. Uh, to heard this or to know this paper, you have to know what attention is all you need. What attention all you need is. This is a famous paper which today we see everywhere. It is applicable from image generation, example DALI, to text processing or multimodal AIs like ChatGPT. Either applied in conjunction with convolution layer or used to replace a certain component of convolution network while keeping their overall structure in place. We show that reliance on CNN is not necessary and pure transformer applied directly to sequence of image patches can perform very well on image classification tasks. When a pre-trained large amount of data and transformed to multiple mid-sized small image recognition benchmarks like ImageNet, CIFAR 10 or VTAB, Vision Transformers attains an excellent result compared to the state-of-the-art convolution networks while requiring substantial fewer computation resources to train. Okay, so if you have some basic knowledge about transformers and attention, you will able to know how this paper basically works. So transformers consist of two main things. One is encoder and one is decoder. In vision transformer, primary encoder is used and there is a single encoder which has its initial patch embedding there, then a sequences are embedded, but an image is divided into patches, then it is flattened and classification token is as inserted before the image, which help us to capture the overall modification in the image, and later that classification token is passed to multi-level perceptron to get the correct result. This is a general overview from my side or what I have understood by reading the abstract. Now let's come to introduction. Self-attention based architecture, in particular transformers, have become a model of choice for natural language processing. Yeah. The dominant approach is to pre-train on large corpus and fine-tune on smaller task-specific dataset. So this is what a transformer learning is basically have been done in computer vision from very earlier, but after the transformers come, it is also possible to do for text like sequences. Thanks for transformer, a computationally efficient and scalable. It has become possible to train a model of unprecedented size with over 100 billion parameters within a model and dataset. With the dataset and model growing, there is a still no signature of saturating performance. Okay, so this is how transformer is not like an sequential. You can say transformers is like in that type of a technology which has a parallel processing ability. So because of parallel processing ability on GPUs, on today's GPUs, it can train even faster. So that's why if you see 300 billion parameter model, so how much parameters are there? In computer vision, however, convolutional architecture remain dominant. Inspired by NLP successes, multiple works are trying self-attention, some replacing the convolution entirely. The latter models, while theoretically efficient, but not yet been scaled effectively on modern hardware accelerator due to use of specialized attention patterns. Yeah. So this basically tells that people in the mid of 2016 and 17 are trying to replace the convolution or trying to connect the convolution with the self-attention model. But the problem here arises that if they do certain type in the certain changes between the architecture may not able to run that model parallel. Therefore, a large scale image recognition classic like ResNet like architecture are still state of the art. Inspired by transformer scaling success in NLP, we experiment with applying a standard transformer directly to images with the fewest possible modification. To do so, we split the images into patches, yeah, and provide the sequence of linear embedding of these patches as the input to the transformer model. Image patches are treated in the same way as token in the NLP application. We train this model on image classification in supervised fashion. Yeah. So to get better understanding of this, I will just tell what is this. Okay. So let's take an image of this, which is taken from the paper. So it's quite blur. Okay, so this is a transformer encoder model. I am expecting that you know this. It's a layer norm layer. Here is a multi-head attention, able to capture the multiple perspective. Usually in attention, it's having 8 heads. Here is an again layer, add or norm layer. It's a multi-level perceptron or a feed-forward network. So this is how a VIT model is. Basically, considering an image like this is image considered like 27 by 27, and it is divided into 3 cross 3 per side of patches. So total there are 9 patches. So after dividing the images into 9 patches of height 3 and width 3, we flatten this image, and it also has an out channels like there are 9 out channels here, and after flatten this it's go to a linear projection for the flattened patches, and each patches there is a positional embedding added, plus here a CLS token is added. So CLS is like a classification token which later the classification token is removed. It is passed to a multi-level perceptron and added with the help of softmax layer we get our given class. So this is a general architecture. Here the transformer encoder is similar to this. So this is how and vision trans is what the methods or the setups they have used for this had discussed. It is not much needed until or if you want to go deep in the convolutions, but from this perspective, it's all fine to see just how the architecture diagram and explanation. Later, this video or next video, I will provide and another video explaining how vision transformer is built from scratch. Okay, so if you see here, this is an input image and this is an attention. So with the help of attention, multiple perspectives are captured from all sides. And because of this, we can get the higher correlation of the main object of that image. So let's come to a conclusion. We had explored the direct application of transformer image recognition. Unlike prior work using self-attention in computer vision, we don't introduce a specific inductive bias into the architecture apart of the initial patch extraction step. Yeah. Instead, we interrupt an image has a sequence of patches and process it by a standard transformer encoder as used in NLP. This simple and scalable strategy works surprisingly well when coupled with pre-training on large dataset. Thus, vision transformer matches or exceed the state of the art on many image classification tasks. So I just want to explain this. Unlike prior using self-attention, we don't introduce any specific inductive bias into the architecture, a part of a patch extraction step. So why this? Okay. So this occur because we are flattening the image. Why convolution operation are basically better for image classification till before this is what when you apply convolution, it moves stride by stride. After moving stride by stride, that current filter or that current convolved filter is able to capture the perspective of its left, right, bottom, and top. But at this case, suppose I have flattened this image. So this image is closely related to this image, but at the end of if I am flattening this image, here it is no relation is developed. So here and such certain this. So they are just telling that at the time of generating the patches from that image, only bias is added and not anywhere bias is added because after the steps are okay, so while these initial results are encouraging, many challenges remain. One is to apply the VIT to other computer vision tasks such as detection and segmentation. Yes, segmentation is quite possible. See, if you see this image, or if you see here, the object is segmented, but not all objects are segmented, but the particular object which has more impact on that image is segmented. Our result coupled with those in crayon indicate the promise of this approach. Another challenge is to continue exploring the self-supervised pre-training methods. Our initial experiment shows improvement from the self-supervised pre-training, but there's still large gap between self-supervised and large-scale supervised training. Further, scaling VIT would like lead to improve the performance. Yeah. So this is only. No need of saying AITs are made from scratch and also how the mathematical operations are performed here. Like how the shapes are modified or how the shapes are getting transformed from this matrix. So once again, a very nice paper from Google Research Brain Drain. It's quite old, like 2021. It's having a citation around 100 or 1000.